Welcome to Lecture 12b entitled Change of Variables in Multiple Integrals. In this case, we're dealing with 3D. So in effect, we're dealing with triple integrals here. So the material for this lecture is covered in section 16.6 of the textbook. And reading assignment 2, particular reference material would be Objective 3, Introduction to Lecture 8 on Jacobians, and a review of parts of Lectures 1a and 1c. Again, reading assignment 2 is not obligatory, but some of the material is taken out of this because it might help you understand how we get these relationships, whereas the book basically just states them and essentially is no derivations provided. The objectives of this teaching module are how to change integration limits and differential volume, which is basically a 3D issue, for triple integrals with a change of variables. And the concepts and visualization skills obtained through this teaching module are the relationship between integration bounds and Cartesian coordinates and the transform coordinates, and also determining the determinant of the Jacobian matrix and the differential volume in the transform coordinates. Again, just as a repeat, it's the previous lecture. In the remaining lecture modules on integration, we use different nomenclature to define transformation matrices compared to what was discussed at the beginning of Lecture 8. And that is to make it more consistent with the textbook. And secondly, you may find Lecture 1a, Slide 6 complementary to the discussion in this lecture. As usual, the second slide is just an outline of the material to follow, so we'll just move on to the next slide. All right, so what I'm going to basically show you that is if you take a differential volume in Cartesian coordinates, which would be dx, dy, dz, and it transforms according to the rules shown, that you take the determinant of the Jacobian matrix and then multiply by the differential volume in the new coordinate system, which means du, dv, w. So general note, differential volumes can be described geometrically as the dot product between one of the differential basis vectors and the cross product of the two remaining differential basis vectors in a given coordinate system. This is the volume of a differential cube. Differential volume at position x0, y0, z in Cartesian coordinates. If you compute the differential volume, this would be just the dot product with a cross product between two differential vectors. So in the xy plane, the differential vectors are dx and dy, and in the z direction, the differential vector is dz. If you take the dot product with this cross product, then that effectively gives you dx, dy, dz, which is the differential volume. The shape of this is a cuboid, and it does not depend on position x0, y0, and z0. All right, now we would like to do a transformation, in which case we are transforming x, y, and z according to three new variables, u, v, and w. The diagram below essentially shows you the relative relationships between these the coordinate systems. So you have the x hat, y hat, and z hat. And you have the new coordinate system with directions, unit vectors u hat, w hat, and v hat. And ds basically is the length, which is just combination of x, y, and z, or u, v, and w. And so what we'd like to do is to figure out essentially how we can determine dx x hat in terms of the unit vectors u hat, w hat, and v hat, and similarly dy y hat and dz z hat. And so the expressions on the right show you how that is done. This is taking the partial with respect to u, partial with respect to v, and partial with respect to w for function g to find the relationship between differential distance along the x hat direction and basically how that's related to differential distance along u hat, v hat, and w hat. You can do that also for dy y hat and dz z hat. Expressions look the same, except in one first case we were operating on g, the second case we operate on h, and the third case we operate on p. So these are basically the expressions for these three differential vectors in terms of the new differential vectors. All right, so now this is the differential volume in the Cartesian coordinate system. We now just do a one-to-one replacement based on the previous expressions on the last slide. And we can see that, for instance, the dx is replaced by this term. And just to make things a little bit easier to package, we just call the components of this vector alpha, beta, gamma, which is the resultant of this cross product between dy and dz. That gives you these terms that you see here in terms of the new coordinate systems, in terms of dw dv, dw du, and du dv. Right, this just makes it a little easier to visualize. So after computing the dot product, in other words, go through this calculation, one can show that the final expression can be written as follows. So this was what we started with in Cartesian coordinate system. And we can show that if we set up a matrix, a 3x3 matrix with these elements, which are basically partial derivatives, and by definition this will be a Jacobian matrix, and then take its determinant, then this times du dv dw, then this is equivalent basically to this expression, which is essentially calculation that would have been done here when things are expanded out. All right, so just in summary, so this is the differential volume Cartesian coordinate system. This is what it would look like in the transformed coordinate system. And the shape of this volume is a parallelepiped, and its shape, which even though it remains as parallelepiped, will depend on the location u0, v0, and w in the general case. All right, so here basically this is doing the same problem but using a mapping. And so I've just mentioned here that one can use a mapping approach to solve for the differential volume, but in this case the position vector will be in 3D, and there will be transformations for x, y, and z as functions of u, v, and w. Again, the volume of the parallelepiped representing the differential volume element dv will be c dot a cross b, where the vectors a and b form the base of a parallelogram, and the vector c forms the height. And so this diagram basically is representing what the calculations that will take place. So a cross b is perpendicular to the plane in which a and b reside in this direction according to the right-hand rule. And you're taking the dot product of this with c to compute the differential volume. And so for side a, this is basically a tangent vector. And so it's dru du, and we can express this in terms of x hats, or I, j's, and k, which are the unit vectors. Again, these are in terms of the partial derivatives with respect to u, where v's and w's are held constant. Here, this is alongside b. In this case, basically, u and w are held constant, and v is allowed to vary. And the last is the case for side c, which is this here. Here's dr dw dw. In this case, the u and v are basically held constant. And so if we do this calculation here, in terms of calculation differential volume, making use of this information, we will find that we can actually also, we can set it up in such a way that it becomes the determinant of a 3x3 matrix involving partial derivatives. But this, by definition, is a Jacobian matrix. And so we end up with exactly the same expression as we had in the previous case. All right, so now we can put all this together in terms of a theorem as a change of variables for triple integrals. Here's your transformation. So x transforms according to u, v, and w, certain functions. Similarly, y transforms according to u, v, w, and z transforms according to u, v, and w. And it's basically a transformation that maps a closed bound region S in the u, v, w space to a region D in the x, y space, z space. Again, we're assuming t is a 1-to-1 on the interior of S, and g and h and p have continuous partial derivatives there. Also, again, the fact that you could have multiple mappings to a given point on the boundary doesn't matter, because the 1-to-1 is only basically of importance within the region itself, not on the boundary. Anyway, if all these conditions are satisfied, then the triple integral basically takes on this form, where x, y, and z are basically replaced by the corresponding transformation equations, so that this now just becomes a function of u, v, and w. And dv transforms according to the expression that you see here, which is the determinant of the Jacobian matrix, dv. In this case, the dv would be in the transformed system du, v, dw. So this now basically describes the transformation that takes place. And the only thing to make you aware of is the fact that in the book, basically they take the absolute value of the determinant of the Jacobian matrix. And the reason is that you do not know offhand when you set up the transformation whether or not you have defined a right-handed or a left-handed coordinate system. If it's right-handed, then the resultant solution for the Jacobian determinant Jacobian matrix will be positive, else it will be minus. But to sort of make sure that it's always positive, an absolute value sign guarantees that to be the case. All right, so let's do a simple calculation. We'll deal with this in more detail when we talk about techniques in terms of how to select transformation equations. So let's look at this particular example. We'll use a change of variables to evaluate this triple integral where D, which is the domain, is a parallelepiped bounded by the planes y equals x plus 2, z equals x plus 3, z equals 0, and z equals 4. Now the solution to this problem is one in which we notice that the D is bounded by 3 pairs of parallel planes, so it makes sense to define new variables which make the limiting bounds on these variables constants. So if you look here, if we take y and subtract off x on both sides, you get y minus x equals 0. And similarly here, you'll get y minus x equals 2. So if you look here, this is the combination. Notice y minus x is the same here as y minus x is the same here. You can do that for z equals x and z equals x plus 3. Bring basically x to the other side, and you have z minus x equals 0, z minus x equals 3. And similarly for the last case, z equals 0, z equals 4. So these two are the same. So it would make sense to define y minus x as one new variable. So that means that you have a bound of 0 in one case and a bound of 2 in the other case. You define z minus x by a different variable, and so the bounds on that would be 0 and 3. And in this case, z equals 0, z equals 4 is already defined. So you really don't have to do anything special here. So what we're looking at here then is basically by replacing y minus x by u, a new variable, z minus x by v, and we'll just say w equals z, just for sake of argument, so that is a mapping. Now this is actually the inverse mapping. Don't forget, when we say x is a function of u, v, and w, that's the transformation t. But this is the inverse, so we define that as t minus 1. Note, when we're doing any form of these calculations, we need both t and t minus 1. So on the next slide, we'll show how the calculation for t is done. Anyway, so these are the basic transformations, and it's clear from that if you let this be equal to u, that means one bound for u is 0 and the other bound for u is 2. Similarly here, the bound for v is 0 and 3, and here the bound on w is 0 and 4, and that's basically explained here. So in fact, this becomes the boundary to region S and points within region S. So what have we done? We've taken this original picture and we've transformed it into this picture. This is much easier to integrate because we're dealing with flat faces. This would be much more complicated. We'd probably have to do some form of decomposition to do an integration, which means we could not do it in terms of one single integral. Just a note, in class 13, we investigate techniques for choosing coordinate transformations with examples provided. As I said, in this slide, we've chosen a linear transformation that converts a parallelepiped into a rectangular box whose sides are aligned with the principal axes and has the same volume as the original object. Hence, triple integration in the coordinates becomes very simple. I mean, that's basically was the objective, to get it into a shape or form which is easy recognizable and can be integrated in one go. All right, so let's now go through and do the calculations. We need the transformation t. So we have UVW is equal to a matrix times x, y, z. So I've taken the previous expressions that we had in equation form and put them in matrix form. So if you were to multiply these out, you'd end up with the same three equations that we saw in the previous slide. Okay, what we want now is t, which means you want x, y, z as a function u, v, and w. So the simplest thing to do is to multiply on the left-hand side on both sides by the inverse of this matrix. And if we do that, then we can get x, y, z as the inverse of this matrix times u, v, w. If you multiply this by its inverse, you get the unity matrix. So that's why it just stays as x, y, z. Anyway, if we basically take the inverse of this matrix, you'll end up with the matrix that you see here. And the next slide will show how we compute an inverse 3 by 3 matrix, just for reference purposes, although this is something that you did in one of the linear algebra courses last year. All right, so if we multiply this out, you can see that x is equal to minus v plus w, which is this one. In the second row you can do, which will be this one. In the third row, multiplying out, you'll get z equals w. Now that we have t, we can compute the Jacobian matrix. It's just the partial derivatives of x with respect to v, u, v, and w, and similarly for y, and similarly for z. And so row by row, if we take the determinant of this matrix, we end up basically with the determinant of this, which turns out to be equal to 1. So the next thing we need to do is to substitute for x and z, basically using these expressions. X becomes w minus v, and z becomes w, and therefore you end up with this expression. Multiplied out, you get this. So that means that the final integral and solution shown here, xz dv, this gets now replaced by omega squared minus vw. This is then the transformed differential volume. And so now we can put in the bounds on the new system. So for u, it was 0 and 2. For v, it was 0 and 3. And for w, it was 0 and 4. And the Jacobian determinant was absolute value is equal to 1. So this just comes du v dw. All right, so first we integrate with respect to the inner integral, and we end up with this expression. And then we basically integrate next round, and finally at the end, having integrated, we get a value of 56. So again, the integration bounds came from the domain where u was limited between 0 and 2, v between 0 and 3, and w between 0 and 4, which is what you see in terms of the bounds on the integration, on the integrals here. All right, and so just to wrap things up, this is just for your reference. This is just showing you how to compute the inverse of a 3 by 3 matrix. What we want to do is prove that the inverse of the matrix, this is equal to this, is given by this. Right? And so what I've done is just taken things which you learned from previous years, that the inverse is defined in this fashion here. And you just carry through and end up with the result which we said basically have proven here. All right, so this ends lecture 12B. Thank you for listening.